So welcome you all to the afternoon session, the last talk of this session. And this is the last talk of Professor Enrique Zuazua lecture series. So Professor Zuazua, you can start now.
Yeah, thank you. Good afternoon, good morning for those that are in Europe. So yeah, yesterday, this is the point we got, right? So we have discussed a lot about the motivation of the problem, the difficulty of recovering already one inversion, of course, even more about recovering all others, even understanding, characterizing, why in some cases there is only one, in some other cases there are very many. How can we characterize the different, say, inversions, right? And how all this is reflected on the numerical algorithms that we have developed. In particular, I emphasized yesterday the importance that numerical algorithms are asymptotic preserving if we want to be successful on recovering the inverse design properly, numerically, right?
Zuazua, can you make the screen full screen?
Yeah. So, and then yesterday I concluded saying, listen, there are a number of things that I didn't yet tackle because actually they are much easier to understand when you are in the context of Hamilton-Jacobi, okay? So, of course, reasons to go for Hamilton-Jacobi are multiple. I mean, we have work as indicated in the top, formula there on the V equation of conservation laws. And then you say, well, what happens more generally for general quasi-linear first-order hyperbolic-like problems? And then Hamilton-Jacobi is a prototypical example of this, right? So just as a mathematical analyst, it's very natural to formulate the question. Now, on the other hand, in 1D, as I discussed yesterday, there is a one-to-one correspondence between Burgers and Hamilton-Jacobi. This is a second reason to do it. And maybe the third reason to do that is that Hamilton-Jacobi is intrinsically related, as you know, with classical optimal control problems through Bellman's principle of dynamic programming, right? We know that one of the main sources of motivation for Hamilton-Jacobi equations is control, right? And nowadays, even though, many people say, well, we don't really do control, actually, everyone needs to do control, in particular in all this move of employing, machine learning algorithms for better do whatever you want to do, even, as I discussed the other day, multiplying matrices, right? So the new algorithms developed by DeepMind to multiply matrices are inspired on reinforcement learning ideas. And as you know, reinforcement learning is kind of a simultaneous treatment of the inverse problem and the control problem, right? So in reinforcement, in classical mathematical applied mathematics paradigms and viewpoints, we said, okay, there is a process in industry or in nature, so we write a PDE for that process. Once you have the PDE, maybe you tune the parameters, you identify the parameters solving an inverse problem. And once you have completely identified the model, then you start playing with it. Existence, uniqueness, asymptotic behavior, numerical approximation, and maybe eventually control. Now, what happens is that in most applications in real life, things don't work that way. We are faced to, the necessity of making decisions about everything in our daily life in a real-time manner, and we don't have the time to, say, first devote, several years to develop the model, the existence, the uniqueness, and the numerical algorithms, right? So we need to act on the fly. For instance, when, I don't know, when you start for the first time learning about how to use LaTeX to write papers, I mean, yes, there is a 500 book with instructions on how to write a paper in LaTeX. Nobody reads the book, right? So you just take, a draft given by a colleague, and then you start reading the draft, and by reading the draft, you understand how this can be done. Probably the same thing could be said about, scientific programming, right? The same can be said if we are offered a new cell phone. I mean, yes, it comes with plenty of instructions, but yeah, this is not the way we do it. We just turn it on and we just enter our PIN and we start operating, and then we learn while we play. So reinforcement learning is about solving simultaneously the inverse problem and the control problem. And actually, in every step, in an alternating manner, whenever you give me more information about the system, I can control better. And whenever I act on the system with a control, and you see the response of the system, this is an information you can use in order to better tune, right? To refine your model. So, and in this way, alternating, you can solve simultaneously the inverse problem and the reinforcement learning problem. And then very often in reinforcement learning problems, you see that someone is behaving, right? So you see someone on the park and you say, well, this person is walking around, is talking, is alone, and you don't understand why this person is behaving that way until you approach the person and then you see, oh, the person has AirPods, and then this person is talking with some relative, right? And then because he's talking with a relative on something very important, he's very focused and he's like, like walking around the square like a zombie in a way that, I could not understand because I don't see any direction in his motion, right? So very often in reinforcement learning, we don't even know what the cost functional is that someone or the process has optimized so to get to this specific trajectory, right? So when you try to understand human behavior, social behavior, even political behavior, when we see these international conflicts, you wonder, I mean, but what is this, this president looking for? What is this president, after to behave that way? Okay. So then in a very simple example is when you have an optimal control problem like on the top, when you don't know what is the final cost, if you try to solve the inverse problem of identifying the final cost on this optimal control problem out of the, the control strategies and the optimal dynamics, then you are in the context of the reinforcement learning, where you need to learn in particular what the cost functional is. And if you formulate that, you see that this is precisely about identifying the initial datum for a Hamilton-Jacobi equation, right, out of the solution at the final time. So you see that this problem of inverse design has a very important additional source of motivation in the context of reinforcement learning. Okay, so now, as I said yesterday, the advantage of dealing with Hamilton-Jacobi is that we can do it simultaneously in 1D and in multi-D. And this is what we did in a series of papers in collaboration with Carlos Esteve, right? We said, okay, let's just go into multi-D directly and try to solve the problem. A scalar Hamilton-Jacobi. Of course, if you go to systems of Hamilton-Jacobi equations that, of course, are very relevant in multi-agent systems, in game theoretical, problems, you don't need to go into the mean field regime, although you can. But even when you are considering, game theoretical problems with a finite number of players, you will get into systems of Hamilton-Jacobi equations and they are harder to tackle. So here we are purely scalar. And we say, listen, what do we want to understand? Well, we want to understand the problem of inverse design, the same as before. And what do we know? Well, we know, of course, there is a classical theory by Crandall and Lyons on viscosity solutions. We know that viscosity solutions for Hamilton-Jacobi are, through this 1D transformation, equivalent to entropy solutions for conservation laws. These viscosity solutions for Hamilton-Jacobi are the limits, right? As epsilon goes to 0, right, of the diffusive approximation. So as soon as we add diffusivity in red on the bottom formula, the problem becomes parabolic. Solutions are smooth. I get bounds. I pass to the limit. And one of the breakthroughs in the theory of Crandall and Lyons was to say, listen, not only you can get one solution by the limit process, but actually there is a kind of test function curious original formulation of the limit that allows you to guarantee uniqueness, like Khrushchev did in the context of conservation laws. Okay? So now when the flux H is convex, when the Hamiltonian H is convex, which is the case I will treat here, you could also treat the same problems, for more general Hamiltonians that are non-convex, and this will be much, harder. This is still mainly open. You enjoy also of the Hove-Lax formula. So you know that the viscosity solution of Hamilton-Jacobi, when the Hamiltonian is convex, is characterized by this Lax-Hove formula that you can use also in 1D for Burger's equation, because after all, the solution of Burger's is just the derivative of Hamilton-Jacobi, and this is what was used by Adi Murthy and collaborators in order to tackle the problem of inverse design for Burger's equation. Okay? Now, what can we do? So the first thing is to realize that when you watch the Hamilton-Jacobi equation as in the top, as I explained yesterday, in this equation, there is no ascent of time. So this is just a first-order nonlinear PDE, right? And in principle, right, this is just first-order relation nonlinear on the gradient of u on x and in t. And it is when we say that I want to solve the Cauchy problem forward that I introduce the notion of viscosity solution forward, right? Viscosity solution forward, as indicated in the, at the bottom of this page, is adding viscosity that is damping the dynamics forward in time, and this generates the viscosity solution forward, right? But in the same way, if I am interested on solving the equation backwards in time, I could say, listen, this equation is purely symmetric in x and t. So I can also solve it backwards in time. The only thing I need to do is to define the notion of backwards viscosity solution. How do you do that? Well, you will come here to the viscous parameter, and instead of putting minus epsilon, you will put plus epsilon, and then you solve the corresponding parabolic problem backwards. You pass to the limit, and the same theory of Crandall-Lyons will tell you there is a viscosity solution backwards. Okay? No problem. You can definitely do that. Actually, you can define also the backward viscosity solution just by playing with changing signs. I can change t into minus t, and then you see that dtu becomes minus dtu, and then you will have a minus in front of the Hamiltonian. So you see that changing the sense of time is also swapping from, say, convex to convex Hamiltonian. Okay? So we have now a forward semigroup. We have viscosity solutions forward S plus. This is the semigroup plus forward. And we have the semigroup minus negative backwards of backwards viscosity solutions for Hamilton-Jacobi equation. And of course, the impact they have on the same datum changes dramatically. For instance, on the left, you see an initial datum that is this kind of M or W-like shape, right, with peaks dotted. And you see on the left the semi-concave solution of, right, Hamilton-Jacobi forward. What does it mean, semi-concave? Well, semi-concave is the Oleinik condition. We said that for Burger's equation, which is quadratic, typically convex flux, corresponding to convex Hamiltonian, we have the condition that ux is less than 1 over t, or c over t, an upper bound on ux. So for Hamilton-Jacobi, this is an upper bound on uxx. And this is what you see precisely, right, on this parabola here. So you see that on the semi-concave function, solid function on the left, which is the output of the forward viscosity solution of Hamilton-Jacobi, you see that indeed UXX is bounded above. Why? It's not bounded below. UXX is not bounded below. Actually, there is a peak. There is a Lipschitz, there are two Lipschitz peaks. At these points, UXX is minus infinity. And this is not a problem. Nobody said that there is a lower bound on UXX, but there is a parabolic, upper bound on USX. So you cannot make this parabola, right, the well, you cannot make this well narrower, because if you will make the well narrower, in particular, you cannot generate singularities pointing downwards, because in order to do that, you will have to do the well narrower, right? And then you will break the upper bound UXX, right? Bounded above. So you see that there might be singularities, peak singularities, where the peak oriented upwards but never downwards. And this is equivalent to saying that for Varga's equation, shock discontinuities are admissible downwards but never upwards. Now, when you solve the backward viscosity solution, you get the reflected shape on the top. I mean, of course, it's not a pure reflection. This is what actually the backward Hamilton-Jacobi equation does out of the initial Darun, which is the same, this M or W shape, right? And again, you see there are, in this case, you see the reverse. The semi-concavity now becomes semi-convexity. It means that the upper bound on UXX now becomes a lower bound on UXX. Therefore, there might be peaks pointing downwards, as we see in the center of this solid, say, shape, right? But there might not be peaks pointing upwards. And upwards, we have a limitation of how narrow the parabola can be, precisely because we have a lower bound on UXX. Okay? So this is elementary, just realizing that for the same Hamilton-Jacobi equation, which is just a naive PDE, you can solve it forward and backwards, and that there are two notions of viscosity solutions, and that, of course, things are different, right? They don't commute. Okay? Very good. So now this is the first clarifying result that you can then also translate to Varga's. It says, give me a function ut, and as I ask you, is this function at the time capital T will be a solution, will be coming out of a solution of Hamilton-Jacobi? Well, the answer is yes, if and only if when you take this measurement you are doing at time capital T, you solve it backwards with Hamilton-Jacobi and then solve it forward with Hamilton-Jacobi, right? Concatenating the backward viscosity semigroup with the forward viscosity semigroup, in case starting from this final configuration, when you move backwards and then forward again, if you get to the same location, then this means that this point is reachable. Whenever this point is not reachable, of course, you will not get to the same point, right? And this gap, actually, the gap of what you get after, this ping-pong strategy, backward-forward, right, strategy, will be a measure of how far you are from the set of reachable targets. Of course, we know that the set of reachable targets, in particular, is conditioned by the upper bound UXX less by C over T. But this is a pure test, okay? Very good. So here, I'm showing you two unreachable targets. For instance, you see, if you tell me that you go to the lake, you measure the solution of Hamilton-Jacobi today, and you got this W on the left, the dotted W, I will do this test, and I will tell you, no, sorry, you are wrong. Your measurement is not sharp. Why? Because if this W were a solution of Hamilton-Jacobi at the final time, I will move backwards, I will go back forward again, and I will get the W. And I didn't get the W. I got, this kind of smooth, rounded approximation of the W, which is on solid lines on the left. Similarly, if another person comes to me saying, listen, this time I did it well. I make a very careful measurement and I got this kind of M-shaped dotted line on the right. Okay, well, because the first time it was wrong, I am cautious. I check it again. I solve the Hamilton-Jacobi equation backwards. I solve it forward. And I see again the same deficit. I don't get the same kind of, M-like function. I get a regularized approximation of that. And then I can guarantee, listen, what you have measured, again, is not, a true solution of Hamilton-Jacobi. The best you can get close to that is the one that is given by the solid lines. Okay? And then, well, the idea of the proof is precisely, realize that, whenever in this commutation of backward and forward, right, whenever there is something left, right, is because you are getting away from the space of targets, of reachable targets. Now, once you get to this point, and this is still something that there is also plenty to be investigated, you see, we have to figure out, we have to think that Hamilton-Jacobi, forward in time, viscosity solutions is a nonlinear semigroup, right? It's a nonlinear semigroup. So we start from a space of initial data, say L1 intersection with L infinity, if you like, okay? And then you take this Banach space of initial data, and this Banach space is moving forward. Now, because the semigroup is nonlinear, of course, you don't necessarily get into a vector space, right? So you are getting into some kind of nonlinear manifold within, or nonlinear set within this ambient Banach space. We know, because this is an upper bound universal, the semi-concavity of solutions of Hamilton-Jacobi, that all elements in this reachable space, right, are, constrained by the condition UXS less than C over T, the same as Oleinik for conservation laws, okay? Now, what we have said is, I would like to understand whether, given a point in this Banach space, this point is inside the reachable set or is outside the reachable set. And I have given you a characterization. A point is inside the reachable set if and only if you solve the Hamilton-Jacobi backwards and then forward, and you get to the same point. In case a point is outside the reachable set, you will solve Hamilton-Jacobi backward, forward, and you will not get to the same destination. There will be a gap. And then the question is, can you somehow characterize, right, this element that you get after backward, forward, right, resolution of Hamilton-Jacobi? Can you characterize this like, say, a projection of the, element into the subspace or manifold of reachable states? Is this some kind of projection? Is, for instance, this the L2 projection? And then we did a test. And then the test show you this is not the case. So on the left, you see again the same experiment, the W element in the Banach space, which is outside the set of reachable states. Actually, in order to check what is the element within the space of reachable states that, that somehow originates out of this W, you solve the equation backwards and then you solve the equation forward, and you get this, solid line regularized version. But when you do the L2 projection, you see that you get something similar but not identical, right? So one of the key questions is, okay, how do you understand this backward-forward resolution from the perspective of, projections and minimization of distances. And this is relevant because, on the other hand, we want to solve optimal control problems. And we would like to know whether I can solve the optimal control problem of approximating this non-reachable state by some kind of backward and forward resolution. And then our remark here is, be careful, because we are dealing here with nonlinear semigroups, so distances are hard to understand, and although things look alike, they are not the same. Okay? Very good. So now let me just show you now a numerical experiment in which we do it in 2D, so to make it more geometric, visually more impacting. So in this case, we did the following experiment. We are dealing with the two-dimensional Hamilton-Jacobi equation, quadratic nonlinearity in 2D. And I would like to know whether this function ut on the left, which is this kind of two cones, these two adjacent cones, this graph corresponds to a solution of Hamilton-Jacobi equation. Well, actually, I don't need to do much work to realize that this cannot be a solution of the Hamilton-Jacobi equation, because in 2D, for the solution of this quadratic Hamiltonian Hamilton-Jacobi equation, I know that the Laplacian has to be bounded above, right? And then when I see that, in these cones on the bases, there are discontinuities on the derivatives on the bases, right? I observe that in those cases, the Laplacian is not bounded above. The Laplacian will go up to infinity, right? Because you have a function like this, like a ReLU, right? Zero derivative to the left, one derivative to the right. You take a second derivative, and this gives you plus delta. Plus Dirac delta is an infinite measure which is not bounded above. Okay? So now I show you what is the output of solving the equation backwards and then moving forward again. And this is what you get. You get the function on the right, which is a kind of upper envelope of the conical function ut, and this is what you get out of backward and forward resolution. You can do that in a video, right? This is the video simulation where you start from t = 1. So you take this final datum, and you want to check whether this is a solution of Hamilton-Jacobi at time t = 1. We know the answer is no, because the semi-concavity condition is broken. But I want to understand whether, how close I will get to this by backward and forward resolution. So I do it, and this is what you see. Backward resolution, from t = 1, I go up to t = 0. This is the initial datum I get. Now I solve forward, and this is what you see. Precisely what is indicated here in a static manner. Okay? So you see again, this is very beautiful, but there are plenty of things to be done in order to better understand, how this gap into the backward-forward resolution can be understood in terms of the geometry of the manifold of reachable data, how this can be used for solving optimization problems and so on. But of course, in all these proofs, right, we are using substantially the comparison principle, right? We are using the fact that, we have the comparison principle, we have the Lax-Hoff formula. So everything you ask about, this kind of Hamilton-Jacobi equations for convex fluxes can be more or less done once you know what you are looking for, okay? So, there is an interesting side result that might be of interest for people interested on obstacle problems, free boundary problems. There is a characterization of the envelope here. You see here on the right that out of UT, I have gotten UT star, which is kind of an upper envelope, right? And you can think, what is this upper envelope? Well, you can characterize this upper envelope by a variational, say, inequality, by a minimization problem in the spirit of classical obstacle problems, right? So this is also a very interesting consideration, because now this means that, well, actually, in principle, out of UT, I have a black box, which is solving this static problem that will give me UT star, right? Without solving backwards and forwards the evolution problem. Well, as we know, things are unfortunately not like this, because even though theoretically I can always claim by this theorem that I have reduced the problem to solving a static, say, optimization problem, if I want to solve this static minimization problem well, I will have to implement a gradient descent algorithm, and in the end I will be doing something which is very similar to backward and forward resolution of Hamilton-Jacobi. Okay? And the last comment I wanted to do about this, and this is very important, especially because we want to go back in the last half an hour to Burgers, is now I would like to explain you, right, what is, so for Hamilton-Jacobi, I have shown you one possible way of doing backward and forward resolution, but now the question is, take a target, okay? Take a target. If this target is reachable, what do I do? Well, you see, when the target is not reachable, my recommendation is, you see, if your target, wherever the target is, do backward-forward resolution. Why? Because in this way, if the target is reachable, you see that it's reachable. You have confirmation that the target is reachable. And then you can wonder, what are all the other possible initial conditions that are leading you to the same target? And in case after the test you realize that you don't get the same thing, then you can say, well, then the target I was given is not reachable. And the best I can do is to approximate this kind of projection that I got by backward-forward resolution. So the problem that remains in the end is, how can I characterize all the initial data in Hamilton-Jacobi that will lead to this target once I know that it is reachable, either because it was reachable from the very beginning or because I made it reachable by projecting into the set of reachable states by this backward-forward resolution. And then this is the answer. The theorem says, listen, if you want to understand the whole class of U0s so that forward resolution gives you UT, a reachable target, then basically what you need to do is first, you take U0 tilde. What is U0 tilde? Well, it's the initial datum that comes out of backward resolution, which is the most natural one. It's the one actually we were computing numerically by Burgers. You recall that I argued that numerics of Burgers will always give you the most natural and most smooth initial datum, is because we were basically doing backward resolution of Burgers in the entropic negative sense. So take U0 tilde. This is the reference one. All other initial data that are compatible with the target are those that are above U0T, and in the set of regularity of U0, in the set where, you know, the solution of Hamilton-Jacobi is just given by characteristics without any collisions and any caustics, any singularities, in that sense, in that set, it has to coincide. So you have then a full characterization of the set of initial data for Hamilton-Jacobi. And this is now when you say, oh, now I understand better. Because in Hamilton-Jacobi, all this can be done by comparison principles, both in 1D and in multi-D. And in particular now, if I use again the transformation between, you know, here, right? If I use again the transformation between Hamilton-Jacobi and Burgers, but this time in the opposite sense, so to go from Hamilton-Jacobi to Burgers, I can say for Burgers what are all the initial data that lead to the final target. Okay, and this is where I want to conclude my lectures, saying again Burgers, again forward viscosity solutions, but also backward viscosity solutions if you want. You can tackle the problem from the perspective of optimal control. But if you really want to have a complete understanding of what is the set of reachable states and what are all possible initial data, right, that lead you to these reachable states, you can do it. I mean, this was done carefully by Colombo and Perrolas in particular, right? But it's very hard to understand in the one-dimensional Burgers equation. However, if you do it through the lens of Hamilton-Jacobi, then it becomes transparent, okay? And in this way, in the end, right, you observe a number of things that maybe you could have anticipated, but that I didn't, right? Let me show you this example. For instance, in this example, right, let me take this one, right? Let me solve it forward. Okay, so you see what we did, right? So you see this example here is giving you what? I taken the Burgers equation now. Recall that I have swapped again to Burgers equation. So shocks propagating to the right? I mean, shocks going down, propagating to the right, but also rarefactions replacing inadmissible shocks that are going up. So I have taken this final measurement for Burgers, this red line, red. So you see, this final target for Burgers has been designed precisely to be compatible with our understanding of what entropic Burgers is. It's a concatenation of rarefaction waves, ramps, and then shocks down. Okay? So in particular, this red broken line here seems to be a good, candidate for getting an approximation of Burgers. Okay? Now, my claim is that this blue initial condition here is a good initial condition that leads to this Burgers solution. I mean, the fact that the blue line has to be like this is easy to guess. Of course, it is much harder to make a good adjustment, right? But it was easy to guess. Why? Because this initial jump upward is the one leading to this rarefaction. This initial ramp downward is the one leading to this shock. And consequently, there is a good fitting. So I do the test, I solve the equation forward, and I see it matches perfectly. Okay, very good. Now, maybe more surprising, I claim that if the target is the same, the red line here is the same, and is the same here, right? Now I have taken a much more chaotic blue signal. I will never have think of this. I will never have thought of this, right? So in particular, if you ask me, you give me this red broken line, and you ask me, please anticipate what the initial data in blue could be, I think I would have given you something very close to this. Qualitatively, this would have been my choice, because it fits perfectly our understanding of Burgers does. But I will never have thought of this for several reasons. In particular, the amplitude of this blue initial datum is much bigger. So why do I need to go up in the initial datum to 2 to get to a target whose maximum is 1. But if you think more thoroughly, you say, and why not? Why not? So you see, we are so much limited by our understanding that somehow we all implicitly, nobody complained when I said that they would have chosen this blue line. In particular, because we are dealing with a forward dynamics that preserves ordering, satisfies the comparison principle or the maximum principle. So if I give you a target, which is in between -1 and 1, like this red broken line, you immediately think on an initial datum, which is also between -1 and 1, because we don't see the necessity of going beyond. That's true, but recall that the Burger's equation is dissipative in the forward sense of time. The solutions of Burger's decay like t minus 1/2. So in principle, therefore, there is no any reason why the initial datum in blue leading to the red target should share the same bounds of the target. And in fact, it doesn't, right? And you see, for instance, this initial datum here, this broken blue line, which goes up to 2, and where now you see there is a concatenation of, now this shock here, of course, you can understand a posteriori the game, right? What I'm doing here? Well, here there was a shock, and this shock became the first rarefaction here. Now I'm doing a much bigger shock, but the shock comes earlier, and in this way, this will also fit, right? And then the other, the ramp here is replaced by this shock. But this shock is calculated with an amplitude so that by Rankine-Hugoniot, it propagates and it fits here. So a posteriori, you can understand that indeed this case will also work. But it's much harder to anticipate. You see in particular how, these shocks are interacting. So the same here on the third. And now let's look to the, to the last one here, down right? And you see that, this is even more chaotic. Why this blue line should be an initial datum that after forward resolution of Burger's, it gets to the correct destination? And it does. Okay? So then you see that what we have done, now all videos together, is we have understood that there are plenty of initial data for Burger's with a complexity that is unlimited and that leads to a reachable target, like the red broken line there, right? And then this can be understood through the lens of Hamilton-Jacobi, where we can say exactly what is the set of initial data leading to the target. Because we are able to do it for Hamilton-Jacobi, we just compute the derivatives, and this is how all these blue broken lines were computed. We just, by hand, design a number of examples that we knew will work for Hamilton-Jacobi, because the condition there is just to be basically above, the most regular possible initial datum that you can compute by backward resolution. You compute the most regular one by backward resolution, and then you take those that are above. You can, draw very, very complicated plots of initial data that will work for Hamilton-Jacobi. And then out of this initial data, you take the derivatives and you get things like this. So what we did was to plot for Hamilton-Jacobi a number of piecewise linear and continuous functions that were, matching the target just by this comparison principle, and then taking the derivatives. of course, by taking the derivatives of piecewise linear functions, you see this kind of piecewise constant jump functions. And this is how this was achieved. Very simply, right? Like, you just do like finite element drawings that fit, the criteria of comparison of Hamilton-Jacobi. By taking derivatives, you can get as many. Of course, we could have taken also initial data that, that are even more complex with bigger amplitude and so on. But I think these experiments show the diversity of possible initial data, right? Okay, so I think that's basically it. I have mentioned a collection of open problems. Let me maybe conclude by emphasizing some of them. First, from a purely analytical perspective, you could say that the extensions to multidimensional scalar conservation laws, to systems of conservation laws, and to systems of Hamilton-Jacobi are, to a large extent, open. That's first comment. All these problems have clear motivations in the context of hyperbolic Burgers-like fluid mechanics. In the context of Hamilton-Jacobi, of course, many of these problems coming from control, game theory, mean fields, reinforcement learning lead to a fantastic class of problems in which these issues are relevant. This is from a purely analytical perspective. Then, more questions is numerics. So understand that developing numerical algorithms to capture well this phenomena is delicate, and that this is related to being asymptotic preserving, right? Other source of difficulties is how to develop numerical algorithms that will be able to give you all this initial data if you don't have analysis at hand, as we did, right? Because in our case, both first in the paper by Colombo Perrolas and later through our understanding of Hamilton-Jacobi, I was able to describe all the set of comparable initial data, but I was able to do it analytically. So the question is, how do you develop numerical algorithms that are able to discover that? Because as we indicated in that, very simple graph, right? The question is really fundamental. There are many initial data on the left that lead to the same target, right? And then the question is now, given a pointer in red, how do you identify whether this point is or not reachable? If it is not reachable, how do you identify the green dot? And then once you have the green dot that is reachable, how you identify all the initial data that are leading to the green dot? Of course, doing backward and forward resolution is always a fantastic remedy. Regardless how complex the problem is, this is what I would recommend. Take the most complicated system in fluid mechanics. My recommendation will be do backward and then forward resolution and see what you get. And probably you will be like in this red plus blue arrow diagram, right? But then if you ask me, could you please tell me all possible initial data that will lead to the same dot, green dot, then that would be very, very complicated. We were able to do it only because we have analysis at hand, right? And yeah, so this is a very, very rich topic. I'm open for discussions. And of course, warning, be careful when you adopt a naive optimal control perspective of saying, well, I will do least square. Oh, yeah, I know the problem is ill-posed, Enrique said, but before Enrique, this was said also by Tikhonov and by Hadamard and many others. We know all these problems are ill-posed. Let's regularize it a little bit. Yes, but for instance, how, for instance, different ways of regularizing the functionals will maybe determine that you are getting to one minimum or the other, right? To one inversion of the other. There are plenty of interesting questions also in connections with optimal control. Okay, and that's all. Thank you for your attention.
Thank you. Thank you, Professor Zuazua, for the nice lecture series. Now I ask the audience if they have a question, they can ask directly, and online participants can ask the question after unmuting them.
Sir, there's an approach to find the viscosity solution by using sub-differential and super-differential, and then proving that viscosity sub-solution and viscosity super-solution. So how this semi-group approach is different from that?
Sorry, can you say your question again?
So in order to construct viscosity solution, that there is a way to find super-differential, sub-differential, and then to prove that it is a sub-solution, super-solution. That's the way also we can construct viscosity solution, right?
Yeah, so but I'm not discussing here about constructing viscosity solutions. Of course, this is a topic that is by now well understood, right? So what I'm saying here is that you can use this notion of viscosity solutions to tackle the problems under consideration.
So
But maybe what you are pointing, and this is a very interesting idea to exploit. This is not something that we really do. I mean, somehow I think it's always embedded in the analysis, but we didn't pursue this idea fully. Maybe what you are saying is, listen, to better understand all this universe of possible initial data that are leading to the same target, maybe instead of being limited by this backward viscosity and forward viscosity solutions, we have to enlarge our search space, right?
Yes,
By looking to super and sub solutions. That's a very good idea. To explore this problem through the lens of super and sub solutions. Although you will be dealing with a problem that we already solved, right? Because implicitly, when you are saying super and sub solutions, you are talking about problems where you have the comparison principle, right?
yes,
And the main challenges arise when this maximum principle or comparison principle fails. But this is a very good point, indeed. Thank you.
Okay, sir. Thank you, sir.
Thanks.
Online. So I have just one question, because every time you are using maximum principle or comparison principle, and that one is essentially used for the single equation. So as you pointed out, that if you have a system of this Hamilton-Jacobi equation, that point of comparison is not there, right?
Sorry, can you repeat your question?
Because for the system of equation, finding maximum principle is difficult, right?
Yeah. So that's, even for reaction diffusion systems, this is a very classical topic, right? In the theory of reaction diffusion systems, semilinear parabolic equations. As soon as you move from a scalar equation to systems, I mean, given, the maximum principle, this is a very, very hard topic, right? So there are some specific constructions of systems where the maximum principle is, you can, of course, preserve the maximum principle, on systems of parabolic equations that are, for instance, in cascade, right? Because you say, the first equation is isolated, I have the maximum principle, then because on the first component I have the maximum principle, then the second and the first component is like a source on the second component, then I will have the maximum principle. Something like this, right? Can be done. But if I give you a fully coupled system of parabolic semilinear equations, well, I know there are, this is one of the topics in which Michel Pierre, for instance, was working, right? But I'm not sure that even in that case, we know everything, right? So now if you give me a Hamilton-Jacobi-like vectorial system, right? I mean, the notation is very easy to extend, right? So out of a U that was a scalar, now you take U1, UN, and then you say this capital U vector, gathering U1, UN, you write time derivative of u plus now you say a big H of the gradient of u, and the gradient of u is now the matrix, right? Because not only you have the vector, the gradient of u with each of the partial derivatives, but you have that for each of the entries of the vector u. So you have a huge now, say, Jacobian matrix. And this nonlinear relation is a Hamilton-Jacobi system. But then I don't even know what is the state of the art in terms of existence and uniqueness of weak solutions, right? Once the theory of viscosity solutions fails, right? So I know this is a topic of investigation per se. People like Nikos Katsoudakis, who is now professor in Warwick in the UK, that was a postdoc in our team some years ago, and so on. They are fully devoted to this topic, right?
Okay.
But now, computationally, you can always do this backward resolution by red and forward resolution by blue. And I think this is what is very often done in engineering, right? Where, well, okay, maybe you don't have a good understanding of that system, but still, you have a computational tool to simulate that system. Probably is based on some, finite volume method with sufficient viscosity built in so that the scheme is stable and so on, right? And then, yeah, this is something you can do.
And just another related question, that you have shown the Barger equation. So suppose as far as I know, for the viscous Barger equation, if you are in a bounded interval, so it has some obstruction phenomena due to the maximum principle or whatever the multiplier by some kind of function. It is, I think the bound was some 1 by t minus x or something like that. So in that situation, if the targets are below that, is there anything known which are the u0 it can reach?
Well, I mean, you still have, so where is it written? Well, I don't know, the Oleinik, oh, here it is. So this Oleinik condition is very robust, right? So, yeah.
No, but this is for written for the entire R, right? But I am saying about the bounded interval.
Oh, I don't know. So in bounded interval, I never looked to this. So I mean, you will have essentially the same thing inside the domain, right? But then you will have boundary effects, right? So then, but you are totally right. So here we have spoken mainly, I mean, that's a very good remark. So here we have spoken mainly about the Cauchy problem on the full line or on the full space. Now, when you put a boundary, then you have boundary effects. And the boundary effects do not affect equally the dynamics in the forward and in the backward sense, right? You remember the first example I gave of ill-posed inverse problem for a linear equation? So this was, I think, the first day. So let me open the slides. I think it was in this set. Yeah, so here it is. Okay, so this is the most trivial example you can think of. It's just linear transport, ft plus fx equals 0. If you just say you are on the real line, there is no problem. This is just pure transport along characteristics. So forward in time and backward in time. It's just a translation. If you give me a time window 0, 1, I know that the initial datum is shifted 1 unit to the right. And the same, if you give me the final datum and you ask me about the initial datum, I tell you very easy. You just shift 1 to the left. Okay? Very good. But now you put boundary conditions because, as you said, Shirshendu is very natural to consider problems with boundary conditions. Normally, in life, there are always boundaries. There are walls. There are limits to the computational domain. in this model, forward transport equation, the boundary condition can be put only on the left, right? Because this is the piece of the boundary. You cannot put a boundary condition at x equal 1, then you make the problem ill-posed. Why? Because, you know, here, the solution here at x equal 1 needs to have the freedom to be what it needs to be, which is transported initial condition incoming from here. So you cannot put a wall condition at x equal 1. You can only put it on the part of the domain in which the characteristics are incoming. And you know that this is true even in the multidimensional case, right? In the multidimensional case, even for a linear transport equation with a smooth vector field, right? The boundary condition can only be put in half, you know, in that part of the domain, on the boundary of the domain where the characteristics are incoming. And you have to let the other half where the characteristics are outcoming free. So then how does this affect the backward-forward resolution? Well, it affects a lot, because when you are doing the backward resolution, the boundary condition has to be put on the right and not on the left. So you see that there is this swapping on the boundary conditions, even in the hyperbolic case, that makes things very tricky. When the problem is nonlinear, things are even harder, because, you know, the formula remains incoming characteristics, boundary condition, outgoing characteristics, no boundary conditions. Yes, but this is thought for solutions that are C1, so that you have a very good notion of characteristics. But what if you are dealing with, say, Barger's equations where solutions might have shocks? So there are early works in the 80s, you know, by Bardos, Nedelec, and so on, which are celebrated about imposing boundary conditions for Barger's-like equations. And this, again, is a topic of investigation in itself. How do you pose boundary conditions for conservation laws, and which boundary conditions make the problem well posed, and so on? Of course, if you now impose these boundary conditions and you reformulate these questions about inverse design, then you get into a new universe of problems. Yeah. And then there are parabolic effects, as you said. Of course, for parabolic, as soon as you put diffusivity, boundary conditions are nice. Just variational theory, classical, say, PDE theory. As soon as you made the problem parabolic, also you have backward uniqueness. So in principle, everything is nice. But of course, computationally, things will become challenging as soon as the viscosity is small, right? Because you know, right, that a small viscosity in practice is very close to pure transport, and you know that something happens for transport equations. And this is, as you know, also one of the reasons why people developed mixed finite element theory, right? Is because the classical, most naive finite element methods, the way we teach them to students, like take P1, do Galerkin, everything symmetric, and so on, these methods have the tendency to become unstable in the presence of boundary layers, something that occurs when the viscosity is small, because precisely we are moving from a parabolic model in which there are two boundary conditions into this one, hyperbolic, in which only one boundary condition is allowed. So then certainly there is a singularity emerging at x equal 1, right? Because in the vanishing viscosity limit, you are losing a boundary condition that was at x equal 1. So you cannot naively say, oh, it's either hyperbolic or it's parabolic. No, I mean, even parabolic, you might encounter many of these technical difficulties of hyperbolic if the viscosity is not sufficiently large.
Thank you. So if there is no other question, let us thank Professor Zuazua for this nice lecture series. And I request Professor Zuazua to send these lectures notes, these slides to me so that we can share.
Thank you. And please let me know if you have any comment or question or suggestion. I will be very happy to discuss it with you. Remind you that we have also in our team here in Erlangen and also in Spain, we have a number of positions and vacancies open, funded by different European agencies. So, you know, if any of you is willing to visit us or come to us for, you know, PhD, postdoc, or just a research visit, let us know. We'll be very happy to welcome you here.
Okay, thank you.
Thank you.